Okay, class, and in this video today we'll understand why there's a pressure inside the fluid, and we'll try to formulate an equation to describe fluid pressure. So inside fluid there's pressure. For example, when diving into water, the deeper the diver goes, the higher the pressure becomes. The weight of fluid on top will exert force on the diver. Fluid pressure results from gravity. So you can imagine when you go to space, there's no gravity. As a result, there's no pressure inside the fluid from gravity, but still fluid can still hold together in space because of the surface tension. Based on the fact fluid pressure results from gravity, we will formulate the equation to describe the phenomena. To do that, we'll first set up an x, y, z coordinate and assume the fluid is in static status, so there's no motion. And we choose a very small rectangle prism fluid element as a free body and denote its left lower corner as xyz. To see it clearly, and the fluid element exaggerated visually with dimensions dx, dy, dz. Again, its left lower corner, its coordinate is xyz. We perform force analysis on the fluid element along z direction, because that's the gravitational force direction. And we know there's gravity, which is downward. Gravitational force equals negative, because it's downward, opposite to the z direction we defined. And then rho, density, times g, gravity, and then times the volume. Well, in this case, the volume also can be expressed as dx, dy, dz. So we end up with negative rho g dx, dy, dz. We also have pressure on top surface, which cause a force, we call it pressure force, Fp1 equals pressure times the area, and point to the downward, so it's negative. And the pressure, we denote the location at z plus dz, and then times the area, and the area also equals dx dy. We also have pressure on bottom surface, and the pressure force this time is positive direction, so it's positive, and the pressure location is z, so we denote it as pz and then times the area, or pz times dx dy. Because it's static, so there's a force balance. Gravitational force plus pressure on top plus pressure on bottom equals 0. And we plug all these values we obtained from previous step into it, we get another equation. In this equation, we notice that dx dy shows up in all terms. We can cancel it. And then we move pressure on one side and rho g term on the other side and divide by dz. And we get this equation here. We write in differential form because dz is a very, very small value. And then p z plus dz minus pz divided by dz equals dp over dz. That's how we define differentiation. In this way, we obtain pressure height relation for fluid, which is dp over dz equals negative rho g. This equation can describe fluid pressure results from gravity. Now we look at what we have. So with the assumption, we assume that fluid is static, there's no motion, we obtain the pressure height relation, dp over dz equals negative rho g. Okay, but we notice that this is a differential equation. We can further simplify it by applying another assumption, and we assume that rho is a constant, or in other words, fluid is incompressible. This is valid for liquid. And then we can move dz to the other side because rho g are both constant, so we can do integration on both sides from location 1 to location 2. And because rho g is a constant, so we can pull it out and then do integration. We'll end up with P2 minus P1 equals negative rho g and then times Z2 minus Z1. I can write in another form and assume that we have fluid, and we choose two locations, location 1, location 2, and we'll have pressure difference equals rho g times h. H is a height difference from 1 to 2. And pressure difference equals P1 minus P2, and P1 is located at bottom and P2 located on top. And then we will get this equation, the pressure difference equals rho g times height difference for liquid.